Hi, welcome to video 14, the first video in section 3. Section 3 is called After the Basics and contains 5 lessons. In this video we're going to take a look at the different methods of positioning, holding or clamping of a component when completing an inspection. We'll look at the practical methods of positioning components ready for inspection and then the importance of documenting any setup completed. Holding and clamping. Prior to any inspection, the component needs to be positioned and held in a suitable manner, as without this, an accurate measurement will be impossible to achieve. Technically, how a component is positioned on the bed of a CMM isn't that important, and all that is required before inspection is for the component, first, be held still and not moved during the inspection. Second, not to rock. Third, allow access to all the measurement points where possible. And fourth, not to be distorted by how it's held or clamped. Hi, welcome to video 15, the second video in section 3, which is called Datum Selection. In this chapter we'll define what a datum is and how they are defined on the drawing. We'll look at the techniques you can use to help you decide what features to use for alignment when no datums are defined on the drawing. Then we'll apply those techniques to an example component. When a datum isn't defined. Unfortunately, not all drawings have the datum as clearly defined as currently shown. Frequently, drawings have no datum specified at all. So what do you do with a component like this? Well, you'll be happy to know that you can't get it wrong as nothing has been specified, so whatever you choose will be just your method of inspection. That doesn't mean your method will be the best or most suitable method. Other people may have different inspection methods that are better suited to the component and its application. Hi, welcome to video 16, the third video in section 3, which is called Reporting. In this video we're going to look at why being in the correct work plane is important when reporting locations. We'll take a look at the difference between polar and Cartesian measurement systems. We'll discuss the angular measurement of features such as cones, and angular positional measurement, including the reporting of 2D and 3D angles. We'll also take a look at the confusion that can be caused when reporting features with a negative position relative to their datum position. And finally, we'll discuss the effect of form error and features not being parallel to the datum in reporting. Example: 4 holes are positioned around a central datum hole, each hole being equally spaced at 25 mm away from the datum. Omitting the Z and the height axis for clarity, the theoretical position in the Cartesian measurement system would be plus or minus 25 mm and 0 for the X and Y axes for each hole. In the polar measurement system, each hole would have a radius from the datum point of 25 mm and angles increasing by 90 degrees for each hole, starting at 0 degrees. In the polar measurement system, the angle 0 position is defined by the work plane and moves in an anti-clockwise direction as described in video 9. Hi, welcome to video 17 part 1, the fourth video in section 3, which is called Programs. Video 17 is split into 2 parts due to the length of the video. In this part of the video, we're going to look at both manual and CNC programs, their advantages and drawbacks. We'll discuss different programming methods, including the learnt and predefined routine methods, and also a common CNC commands and parameters. We'll look at the different ways of moving around the component, including the use of safety planes and explaining move and hit vectors, describing their use and potential errors. Measurement start. The distance between the theoretical hit point at which the CMM changes between the move and measure speed. Measure 4. The distance after the theoretical hit point for which the CMM will continue searching for a surface. Retract 4. The distance the probe will return once a hit has been taken. Safety planes. An alternative method of navigating around the component whilst in CNC mode. Safety planes remove the need for the majority, if not all, move points and simplify programming. Hi, welcome to the second part of video 17, the 5th video in Section 3, which is called Programs. In Part 2 of Video 17, we're going to look at automation and how simplified alignments help with the simplification of CNC CMM programs, reducing the necessary skill set for production inspection. We'll look at 2 examples, the first creating a single point start program and the second a 0-point start program. Finally, we'll look at general programming tips, including the importance of operator comments and the naming convention of features. The current image shows the door handle component from video 15. For this component, the drawing may specify a datum on the top face and running through the center lines of the hole and the slot, this being created using the plane circle slot alignment method. The simplified alignment could be created using a plane line point alignment. The plane would be measured on one end of the top face only, and all features would be measured using a minimum number of hits. Once this alignment has been completed, CNC mode can be engaged and the full drawing alignment undertaken. Hi, welcome to video 18, the 6th and final video in Section 3, which is called Working with CAD. In the video, we'll define what a CAD model is and the advantages and disadvantages of using them. We'll look at the different formats of CAD models and good practices when converting between these formats, and also the importance of determining if the CAD model is master. We'll look at offline programming and how it reduces online programming time, but also the difficulties when taking the new program online. Finally, we'll look at an alternative method of reporting, this being the reporting of surface condition. CAD Master. Before CAD models are used, it's important to determine if the CAD model is the master. Most components have a drawing that defines the geometry and size of the component. The drawing also specifies the tolerances to apply to these features. When there is a CAD model, it's common for the model to override the drawing. The model is taken as being correct when differences between the model and the drawing are found, hence the model being the master. When the model is the master, it's common for the drawing to have a comment specifying this.